Good evening, everyone. Welcome back. It is our October Speakers Night for 2025. Welcome to RASC Toronto Centre. We are online tonight, and I am Dr. Elena Hyde, the second Vice President of RASC Toronto Centre, and I am joining you tonight for actually I think this is my first broadcast for Halloween as a Canadian. So, yay. Welcome, everyone. Our speakers night presentation will start off shortly. Please note that this meeting is an online only presentation and not at our New York University meetup location. Our president, Scott Masterton, will be talking about our various programs later on this evening. But first, before we get started too much, we'll have a little bit of a special event to kick off. So let's go ahead and start off in our usual manner with a little bit of a land acknowledgement. I'd like to acknowledge that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the earth. Now, to introduce our fantastic speaker for tonight, we're very lucky to have Dr. Patrick Hall. He's an astronomy professor at York University who studies quasars, which he's going to tell you all about, I'm sure, these distant supermassive black holes of intrigue. He sponsors York graduate and undergraduate students to do research at York University. He uses the Sloan Digital Sky Survey, which a lot of folks here will, I'm sure, have heard about. I will let him tell you all about this interesting investigation and beyond our Milky Way, the distant galaxies. His research team and collaborators, if you're interested, are surveying quasars for outflows, looking at time variability, and comparing them to computer simulations. Dr. Hall has also developed a unique astronomy workbook for use by our undergraduate students at York, and he's done many public talks. So we are very lucky to have him tonight. This being our October 2025 Speakers Night, I am really looking forward to this haunted topic. Spookier than the Witch's Head Nebula, higher power than the cat's eye. Um, and actually, as a total first for my tenure as RASC Toronto Centre Speakers Night MC, Dr. Patrick Hall is going to tell us about an object so amazing that I named my cat after it. Pat, please take it up, up, and away.
Thank you very much, Elena, for that introduction. Welcome, everyone. I'm glad you're here to hear about quasars. So let's get right into it. I'll be talking a lot, but you'll be able to review it later if you want. So let's start off with the simple question. What is a quasar? Well, as far back as the 1940s, the centers of some galaxies were noticed to be relatively quite bright. So if we just take a look at an image, on the left, we have a spiral galaxy, normal spiral galaxy. But on the right, we have a spiral galaxy with a very bright center, a very bright nucleus. And this became known as an AGN. So that relatively quite bright center was also seen to have very broad emission lines in its spectrum. So a spectrum is just science jargon for rainbow. It's all the light of an object spread out into its constituent wavelengths. And when astronomers took spectra of these galaxies, they dubbed this class of galaxy an active galactic nucleus, or AGN. So galaxies that have central activity. And a quasar is just a very luminous AGN, an AGN that's putting out a huge amount of light into the universe. So we're celebrating over 60 years of quasar science at this point. Quasars, these luminous AGN, were at first a mystery until an astronomer named Martin Schmidt identified them as extremely distant objects. Uh, we don't consider them the ones he was looking at. They're not really that distant compared to what we know now, but at that time it was really remarkable, as you can see by his making the cover of Time magazine. So that's what a quasar is. But what causes a quasar? Well, the best way to think about this, I think, is to think of a quasar as a process, not a thing. So it's the process of what happens as matter spirals into a supermassive black hole through an accretion disk, and the disk launches an outflow. You've probably heard about black holes, maybe even accretion disks. They go together, but the outflow also goes together. It seems naturally that material spiraling into a black hole, well, black holes are messy eaters, and some of the material is flung back out into space. So, what is a black hole? Let's make sure we all remember. A black hole is an object with an escape velocity greater than the speed of light. And that just means that because nothing travels faster than light, nothing can escape a black hole. So black holes have mass, they have spin, and they have electric charge, and that's it. In astronomy, we don't worry about electric charge because a positive black hole would attract a negative charge and go back to being neutral. So we only have to worry about mass and spin. And the mass of black holes is their most important property. Now, mass, we're familiar with mass. The Earth has mass, the sun has mass. The Earth orbits the sun due to the sun's mass. The Earth could orbit a black hole. It's not a problem to orbit a black hole. But the closer you get to a black hole, the closer anything gets, the faster you need to move to stay in orbit. And if you get close enough, there aren't any stable orbits. Close enough to a black hole, there's nothing you can do. Uh, you, I should say, you can't orbit. You will spiral in. So if you get within the black hole's event horizon, you'll never be able to escape because you can't travel faster than light. And for non-spinning black holes, this event horizon is located at the Schwarzschild radius, named for Karl Schwarzschild. I always hold off showing his photo due to his distracting mustache, but that was Karl Schwarzschild who came up with the simple equation, and I'll only show like one or two equations. Uh, the Schwarzschild radius is twice the gravitational constant times the mass of the black hole divided by the speed of light squared. And so that makes black holes strange because the Schwarzschild radius increases with the mass of the black hole. You double the mass, you double the Schwarzschild radius. And for the sun, the Schwarzschild radius is extremely small, only 3 kilometers. In other words, to make the sun a black hole, you'd have to squish it down to something 3 kilometers in radius. But for some of the most massive black holes, the Schwarzschild radius is about the distance of Uranus from the sun. And that leads to uh, a concept that has been dubbed spaghettification in a very scientific term. And this is just referring to the fact that if you approach a black hole, not recommended, but if you did, your size relative to the event horizon matters. So if we imagine approaching the event horizon of a black hole with the sun's mass, you will be pulled apart before reaching it because there'll be much stronger gravity at your feet than at your head. Uh, Even that small difference of 2 meters relative to 3 kilometers, it's enough that the gravity will be very different and you'll be pulled apart. But if you approach the event horizon of a black hole with 1 billion times the sun's mass, you could cross it in your spaceship, presumably, without being torn apart. The gravity would be insignificantly stronger at your feet because you're at the distance of Uranus, let's say, from the sun, and there's just no significant difference between gravity at your feet and at your head. So you can dive into a black hole if you wanted to, you just would never be able to get back out from one of these supermassive black holes. So that's what black holes are. It's cool to think about them, but do they actually matter? Well, we've learned that they do because every massive galaxy has a central black hole. And most black holes around us in our local universe are not accreting significant matter now, but they must have done so in the past because that's how they must have grown to their current masses. And powerful outflows during those growth phases affected the formation of the surrounding galaxy. We can't understand galaxies without understanding how their center black holes affected their growth. So I told you that every massive galaxy in our local universe has a central black hole, but you should be asking, well, how do we know this? Well, the best evidence for a black hole comes from the center of our own Milky Way galaxy, where we can study the orbits of stars around a dim object called Sag A star in the constellation of Sagittarius. And now Nobel laureate Dr. Andrea Ghez, her group at the University of California, Los Angeles has done this, along with other groups, finding that Sagittarius star has a mass of 4 million suns. And the way they've done that is by studying stars, the orbits of stars around Sagittarius A star. So you may have seen this before, but I'll play it again. Each of these is a representation of a star, has a label number, and you'll see them. Here's the date back in 1995. You'll see them move in their orbits, and you can watch the date at the upper right. There's the position of the black hole. And stars can come in plunging orbits, elliptical orbits, and make sometimes complete orbits around the black hole. And by measuring how the stars move in these orbits, how fast the orbits are, we can work out 4 million times the mass of our sun is contained in this little spot here, which really is giving off very little light. So we know that black holes exist. We know that every massive galaxy has a central black hole. And we observe that there's a rather tight relationship today, 13.7 billion years after the Big Bang, between black hole mass and host galaxy mass. So a more massive galaxy has a more massive black hole with some scatter, some randomness there, but it's a pretty tight relationship. And we think the reason for that is that feedback from accretion onto the black hole shuts down the growth of the black hole and that of the host galaxy. So the black hole and the host galaxy are growing, and then the black hole has an episode of feedback that shuts everything down. That's our current working theory. And we have simulations where we can test this. So three astronomers, DiMatteo, Sprengel, and Hernquist, shown here, simulated the fueling of quasars during the merger of two disk galaxies and the effect of that merger on the galaxy's gas, not the stars. So that's what I'm going to show here, the simulation that they produced. Two galaxies, and again, we're only showing the gas, two spiral galaxies. The color coding is the temperature of the gas. So you'll see what happens when the gas of the two galaxies uh, runs into each other. Shock waves and very hot gas. And tidal forces distort, and gas now starts falling into the very center of these galaxies where black holes lurk. And you'll see something interesting start to happen as the black holes at the centers of these galaxies are fueled. You can see gas starting to billow out from the centers. The gas that has plunged into the center has fed the black hole, and black holes are such messy eaters that they're expelling almost all the gas. Now, these two black holes will eventually merge, and accretion onto that merged black hole really takes off and can, in fact, effectively blow out essentially all the gas in the galaxy. You can see there's still a little gas in the center there, and we don't need to see the whole thing because have seen the uh, you've seen the main story. So these mergers of galaxies with their central black holes, as you can see, have a real big effect on the gas in the galaxy. We didn't show you the stars in that simulation just to focus in on the gas. The stars are fine. The stars form a galaxy. Two spiral galaxies form one elliptical galaxy, but all the gas is blown out, and no more star formation means the mass of the galaxy doesn't change. So let's go back to talking about what's happening close to these black holes at the centers of these galaxies. So as I've mentioned before, the closer you get to a black hole, the faster you need to move to stay in orbit. Well, if you imagine a cloud of matter approaching a black hole, it's going to be stretched and torn apart. The gravity being stronger closer to the black hole is is an example of what we call a tidal force, and that will stretch the cloud of matter and tear it apart until it settles into a flattened accretion disk around the black hole. So this accretion disk around the black hole, that's a quasar. There's more to it, but that's the basic point. The accretion disk, not the black hole, is what we see. So that's why my title has the quotes in it. Quasar is a black hole we can see. So this is a picture of inferred quasar structure, and I keep thinking I should find a better picture, but uh, uh, this still gives the basic idea. We have a black hole at the very center and a thin accretion disk, which may puff out a little closer to the black hole and flares out into this torus at larger radii. And from the black hole, we sometimes see these very narrow jets traveling at nearly the speed of light, and we see gas clouds flowing out, which I'll talk more about later. So this is inferred structure. This is an actual image of one of the jets in a nearby AGN M87. So a black hole, an opaque accretion disk of inspiraling gas, these polar jets that I won't really talk about, even though they're cool, and outflowing gas clouds, some in a wind across a wind that comes off the accretion disk. So I want to take a small interlude here and talk about uh, the way accretion disks would actually look if we could. So if we could see them, gravity distorts the space around a mass, and black holes have huge masses, so they distort the space around them a huge amount. So objects no longer move in straight lines near a mass. For example, orbits are just distorted paths in the distorted space around a mass. And this even applies to light. So we don't really notice it with the sun. It's a very small effect. But with the strong gravity of a black hole, the image of an accretion disk we could see is distorted, especially if the black hole is spinning. And the movie Interstellar showed this distortion accurately. And here's the accretion disk around the black hole in Interstellar. And you can see here's this disk-like structure, but what's this ring there? What's going on with that? Well, these diagrams show that a little better. So here's an accretion disk seen nearly face on, where we've shown different areas of the accretion disk in this checkerboard pattern, and it looks fairly normal. But if you tilt the disk to see it near the edge on, well, here's this near the edge on part of the disk, but this is the part of the disk that's behind the black hole. So it's literally behind the black hole. If we didn't know about the effect of gravity on light, we wouldn't be able to see this. But the strong gravity of the black hole essentially bends the light around. This light was heading up towards the top of the page, but it got uh, bent towards us. And this down here is the bottom of the accretion disk, which is something we wouldn't normally be able to see. But again, the strong gravity of the black hole brings it in that light into our line of sight. And a spinning black hole actually takes these areas and distorts them and uh, can have a similar large effect on the area of the accretion disk behind the black hole. And part of the accretion disk gets brighter, which is present in this image, but is a little hard to see. Uh, the Interstellar movie had physicist Kip Thorne from Caltech as a consulting producer, I think, and he helped them get this image of this accretion disk uh, pretty accurately. So this is what an accretion disk might look like if we could actually see it up close, but we'll have to settle for seeing the light from these accretion disks as quasars, and I'm very happy to do that. So if we want to image a black hole, well, we can't. Black holes don't emit light, but we can look at the bright material around a black hole. And for a quasar, that material can be seen in optical light and ultraviolet light. But in our own Milky Way, all the gas between us and the dust between us and the center of the Milky Way means we can't see the Sag star in any optical or ultraviolet light. We need to look in infrared and radio. And that's great because the Event Horizon Telescope used radio telescopes to test Einstein's theories of gravity and black holes with the shadows of the two closest supermassive black holes, SMBHs. And I'm sure you're familiar with these images from the Event Horizon Telescope using telescopes around the world, radio telescopes. Uh, Using computers to treat the radio waves they observe as if they were observed by a telescope this size, and have these images of Sag star on the bottom and M87 on the top. The spiral patterns are the polarization, which helps understand um, the accretion in great detail. And so here's the black hole in the center, no light coming from it, but we're seeing the shadow essentially of the black hole, the light around it, but not the black hole itself because black holes don't emit light. Okay, so black holes are cool, but quasars are even cooler. So quasar, again, it's a process, not a thing. It's this disk of matter spiraling into a supermassive black hole. And this matter in the disk heats up through a kind of friction. So faster orbits near the center mean hotter temperatures near the center. So different radii, different distances from the disk glow at different temperatures. Ultraviolet light comes from small radii, infrared light comes from large radii, and optical light comes in between. And this accretion disk seen in this NASA illustration can emit as much light as 10 quadrillion suns, a huge amount of light, because this disk is huge. And so it's a disk much bigger than the surface of our sun. It's more like the size of our solar system, and it's hotter than the surface of the sun, which is why quasars are so bright. And if you think about something the size of our solar system is bright or brighter than the surface of our sun, that's a huge amount of light. And the ultraviolet light in particular can actually launch material off the disk. And here's Canadian content, which I'm very happy to share. So this possible accretion disk structure, which I'm going to show, is an idea from Dr. Norm Murray at CETA here in Toronto, and the figure is from a paper by my colleague, Dr. Sarah Gallagher at Western. So here's a little sketch, the kind that astronomers do to help us try and figure out what's going on in quasars. So very near the black hole, there's an area that produces X-rays. Farther away, ultraviolet light, optical light, etc. But the X-rays come from very close to the black hole. And those X-rays travel out, and what if they encounter some shielding gas? This parcel of gas, which absorbs the X-rays. So the X-rays have the ability to take an atom and strip all the electrons away. And if you lose the electrons, you can't scatter light and be accelerated into a wind. So what happens, we think, although the details are still an area of great debate, shielding gas absorbs X-rays, and then a wind is launched by ultraviolet light. And we call this wind a broad absorption line wind, or BAL wind. This BAL wind is launched, and it may end up forming something like this red square nebula. Now, this is a disk wind of a different type in our own galaxy, but it's still coming from an accretion disk around here, just not around a black hole. And you can see that this sort of double funnel structure is a wind coming off an accretion disk, and we think something similar is happening in quasars. So I'm particularly interested in BAL quasars. So I'm going to tell you today these strange science stories of redshifted BAL quasars from outer space, as well as some other exciting things that myself and other astronomers have discovered. Okay, so just a reminder, quasars are emitting and absorbing, um, they're emitting light. And because we have light at different radii, at different temperatures, we have a spectrum which is not just one color, but is emitting light at all colors. So it's a white light source, and there are emission lines in the quasar spectrum which are about 10,000 kilometers per second broad. And that just means that the gas around a quasar is traveling at 10,000 kilometers per second. In order to orbit the black hole, that's the characteristic temperature it needs to have. Our Earth, sorry, is going around the sun at 30 kilometers a second. We're talking 10,000 kilometers per second in quasars. And about 1 in 4 quasars have broad absorption line troughs, thousands of kilometers per second wide, from gas that's flying off the accretion disk at up to 30% the speed of light. So the speeds in these quasars are really incredible. Okay, so now we're getting into some cool science stuff, but I have to walk you through it. This is a spectrum of a quasar, or actually a spectrum of an average quasar. So what I'm going to show in 3 or 4 cases here is a plot of the amount of light we get at different wavelengths from the quasar. So blue light on the left, or shorter wavelength to be technical, shorter wavelength light, and longer wavelength light. And a quasar is very hot, so it has more blue light than red light. So it's higher on the left than the right. And it has these broad emission lines, these smooth features from gas whipping around the quasar at incredible speeds. And a BAL quasar has the same thing, usually, same spectrum with these broad lines, but also it has absorption. And that absorption is blue shifted, meaning that you look at the line and to the left of the line, there's absorption. That means the gas is going from the quasar towards us and is blue shifted, shifted towards shorter wavelengths. And I'll show why in a second. But sometimes we even get these reddened BAL quasars where we think there's dust in between us and the quasar, and so the quasar looks very red. Okay, so let's talk about this Doppler shift. So the Doppler shift that causes blue shifting is revealing the speed of gas towards or away from us. So here's an example. Earth is over here on the right, and we have these 3 objects, let's say 3 sodium lamps, that are emitting medium wavelength yellow light. So here's a lamp emitting yellow light, and it's not moving towards Earth or away from Earth. So it's emitting light of a certain wavelength, which is yellow. But if we have that same sodium atom moving towards Earth, then it's going up and down at the same rate, but its light becomes blue shifted because it's moving towards us. And another lamp moving away from Earth, all these 3 lamps are, all these sodium atoms are still vibrating at the same rate, but because it's moving away from us, it's producing red light. So longer wavelength, lower energy, red shifted light, and higher energy, shorter wavelength, blue shifted light. And so when we see blue shifted absorption, we know the gas is coming towards us. So that's been known since almost as soon as quasars were discovered. We found that some of them were having this absorption. But about 1 in 1,000 of these quasars, of these BAL quasars, so about 1 in 4,000 quasars overall, shows red shifted absorption from gas which is moving away from us towards a quasar. So here's an unabsorbed quasar spectrum, and you can ignore everything, all the labels. All you need to remember is blue light on the left, short wavelength light on the left, long wavelength light on the right. There's more blue light than red light, and these broad emission lines. And now let's put up this quasar with red shifted absorption. Well, sure enough, when we look at a broad emission line, the absorption is to longer wavelength, red shifted instead of blue shifted. So now we have a quasar which is showing uh, red shifted absorption, gas going away from us, falling into the quasar. And no one predicted that gas falling into a black hole would look like this. And we still don't know exactly how this happens. It could be the simple explanation that it's just gas falling into the quasar, but that's actually really hard to work out in detail. And so we think it's due to a rotating disk wind. So it's still a wind flinging gas away, but it's rotating. So the first scenario, this is an illustration I came up with just to show the idea. Here's the inner part of accretion disk. It's glowing, very hot, and gas is falling in, and it's producing red-shifted absorption. So the arrows show the way it's moving, and the colors are showing you it's red-shifted because it's falling in and moving away from us towards the quasar and the black hole. Or it could be rotating wind. Because if a wind is rotating when it's launched, you see these arrows here, they're showing the rotation. The gas is rotating and starting to move out. But when it starts, it's still, part of it is still moving away from us. So it could be that we're seeing some redshifted absorption from the same wind that is actually flinging lots of gas out into space. It's uh, it's a matter that's still under investigation. I really hope to do some more work on this sometime soon. But in the meantime, I got distracted by this other cool thing I found, this other cool quasar. So most broad absorption line outflows have velocities less than 10% the speed of light. But there's a category which have recently been dubbed extremely high velocity outflows at greater than 10% the speed of light. And back in 2016, as my student Jesse Rogerson and I found one that was moving at 20% the speed of light, 20% of C, 0.2 C, 20% the speed of light. And my current student Lucas Seaton and I now have the new record for the fastest outflow discovered in the ultraviolet and a tie for the fastest overall. And this uses data from the Sloan Digital Sky Survey Mark V, which I'll talk about. And again, here's another spectrum where you can ignore everything except remembering that short wavelengths on the left, long on the right. Here's the only real obvious broad emission line. The spectrum is not as blue as usual. Here's where here's where the absorption should be, but it's all the way over here. That's because it's moving at 80 to 90,000 kilometers per second. It's reaching 30% the speed of light. And this used the Sloan Digital Sky Survey for everything on the left half and a follow-up infrared spectrum with Gemini on the right. So I've just alluded to it, but where do our ideas come from? I've shown you some cool stuff about black holes and quasars, but what data do we use to come up with these ideas? And more importantly, how do we check that they're correct and figure out something new when we realize they're not correct? So I work with the Sloan Digital Sky Survey. So this uses a 2.5 meter diameter telescope at Apache Point in New Mexico for its traditional survey, and another telescope at Las Campanas Observatory in Chile for the new SDSS 5. So the original Sloan Digital Sky Survey was a digital survey of 25% of the sky in 5 bands across the optical bandpass and spectra of, by now, over 1 million stars and galaxies and over 500,000 quasars in the optical. And it's been going for 25 years now. It's in its SDSS 5 phase, which includes a project called BHM, Black Hole Mapper. And that consists of spectroscopy of quasar candidates and known quasars. The 30% of the speed of light object I showed, that was a known quasar, but its outflow was not obvious until we got a new spectrum and figured it out. So another Time magazine cover here of Alfred P. Sloan, who made a lot of money in the automobile industry, and his foundation continues supporting science today. So the way the Sloan Digital Sky Survey works uses optical fibers, which some of you may be old enough to remember these vintage optical fiber home decorations. I'll show where they come in astronomy in a moment. Light is sent through these fibers to a diffraction grating, which is just a more efficient prism. Light bounces off of it and is separated into different colors. So light of different wavelengths is sent in different directions, and we can record different wavelengths at different points and measure the spectrum of a quasar or a star or galaxy. And we do that using a telescope like this one. This is the SDSS telescope. The dome covering is rolled off to the left out of sight. And at the back here, when this telescope is doing spectroscopy, used to be a plug plate. This is a metal disc full of holes, and optical fibers were plugged into the holes. And each hole would be designed to be at a position where there's a star, galaxy, or quasar there, and we collect their light and study their spectra. So each plate was drilled in a precise position to capture light from a specific target that had been traveling to Earth for thousands of years for a star, millions of years for a galaxy, or billions of years for a quasar. But since 2020, we've moved on away from those plates, and we now use robotic fiber positioners. So that's seen here. You can't really see, there's the tip of the optical fiber is right here. You can't see, but this is a double rotation scheme where this part can rotate around, and then the whole thing beneath it can also rotate. So all of these can be positioned not in a regular array like this, but in an array such that we catch the light from wherever we want to look on the sky. And this allows us to change our mind and go look at a new position in the sky if we want, if something cool is happening there. We don't have to, have a plate prepared in advance. So that's what I use, a 2.5 meter telescope and an 8 meter telescope for follow-up work. But soon we will have larger ground-based telescopes. Today, the largest telescopes are on the order of 10 meters, such as the Keck. Uh, in the next generation is on the order of 30 meters. So the European Extremely Large Telescope is under construction. The Giant Magellan Telescope is probably going to happen. The TMT is anyone's guess, but that's a whole other talk. So let's not worry about the future. What have we got today? We've got the James Webb Space Telescope, an excellent telescope in space. And Canada is a partner in JWST through the Canadian Space Agency. And my colleague, Professor Adam Muzzin at York, got the largest ever allocation of time on JWST in the last proposal round. So elbows up. Now, JWST is a 6.5 meter telescope in space, and it works in the infrared from just at the reddest wavelengths we can sort of see with our naked eye, all the way out to 27 microns, which is it's real infrared. And its diameter gives a large collecting area and a sharp PSF unaffected by the atmosphere since it's out in space. And all this means that we can now study faint galaxies and quasars at a time when the universe was less than 1 billion years old. Because the expanding universe, means that when we look at the most distant quasars and galaxies, we're seeing light which has been redshifted due to the expansion of the universe by a factor of up to 10 or even a little more. And so uh, needing to go to long wavelengths to study quasars and galaxies in the early universe. And JWST discovered something called little red dots, or LRDs. And these is the best guess we have is that these are quasars we can't see because they're hidden through a lot of dust and gas, or quasars we can barely see. So again, here's another spectrum, and again, ignore everything except the general idea. Short wavelengths on the left, long wavelengths on the right. And here we've got this sort of mixed messaging going on where we have something that looks like it might be a quasar over here on the left. It's got more blue light than red light, and it's got a broad line. It's a little hard to see here, but this is low resolution, so this is actually quite broad. And here's another broad line over here. But so what's going on with this reddened part here? Well, we're not sure. We know that little red dots are unresolved, so they must be physically small. They're red due to high redshift and a break from excited hydrogen absorption. And this break just means less flux at short wavelengths. So what we think is going on here is that this is there's lots of dust and gas in our way, and like that reddened quasar I showed you earlier, this gas is uh, the gas is getting rid of most of the light, but some of the light is peeking through. They have broad emission lines, so black holes, we think naturally, but they don't have X-rays and they don't have far infrared light like normal AGN. So for a while, people were thinking, well, maybe these are ultra dense galaxies, but those would actually be so dense that the stars would be colliding and that we should see X-rays. So that doesn't seem to work. So we have this idea now of a black hole star. So if a black hole accretes at an extremely high rate, this disk, you can't form a thin disk. The disk puffs up and it keeps puffing up until it's maybe even just a sphere. And photons can get trapped in the innermost 40 AU or so of the outflow. So again, this is a spectrum here. It's reddened, and we have data and a model. But I really showed this figure from a very recent paper just to show this idea here of a dense black hole, a region where maybe there is a disk and it's creating emission, but this blue region 40 AU thick shroud of gas and dust that all absorbs all the X-rays, absorbs all the UV, and just outputs it as um, optical light. So this black hole star idea is supported by some data, such as this data here, through gravitational lensing of a little red dot at redshift 7. So this is the Abell 2744 galaxy cluster with JWST. Um, I'm going to ask you to focus on this left part over here, where there's sort of something you can think of maybe as a face. There's a little mouth, a nose, and two eyes. So let's zoom in. Yep, there we go. Mouth, nose, two eyes. Where's the little red dot? Can you spot it? Well, it's right there. And this little red dot, see, here we are again. We've zoomed out. So here's the mouth, here's the nose, here's the two eyes, and right between the eyes, this little red dot. That's actually one of three images produced by gravitational lensing, the bending of light by gravity, of the same little red dot. And JWST was used to study its hydrogen line emission that was actually spatially resolved because gravitational lensing magnified, it brightened and it magnified. So we have higher spatial resolution. And here's what we see. This is a tiny bit of space, zero point 0.1 arc seconds across, but we see that some of the gas on one side is red shifted moving away from us, and some is blue shifted moving towards us. And how fast it's moving away from us and towards us is such that it's better fit by a point mass than a galaxy. It looks like this is just a black hole with gas around it and no stars around it. Now, we're all pretty sure there are some stars there, but the point is it's a tiny amount of stars. This black hole has is much more dominant relative to its galaxy than what we see in around us in our local universe today. So little red dots are a big deal. It's really hard to make, just as an example, a supermassive black hole of 10 million solar masses at redshift 7, only 765 million years after the Big Bang. You could still do it though. If we found one, it wouldn't worry anyone. But there's a lot of these LRDs. And so it's tough to think how can we make so many of these black holes, which have gotten very big much faster than their galaxies have built themselves up. And that's the big question. Today was, or maybe is, the still the deadline for proposals for the next cycle at the James Webb Space Telescope. So some of my colleagues, I'm sure, are frantically finishing their proposals to get time to figure out what these LRDs are and how these black holes assemble so much faster than their host galaxies, and why some accreting black holes look like LRDs and why some accreting black holes look like normal quasars. We have ideas that I've shared with you, but this is very much an area of active research. It may be that these are very high accretion rates. So the gas is just piling up and causing something that doesn't look like a normal quasar. And maybe to get that, you need to start with a massive black hole that in fact gas clouds might be able to collapse directly to form a black hole of thousands or tens of thousands of solar masses. Um, and if they can form that quickly, then maybe that explains why we see so many of them not too long after the Big Bang. So stay tuned. Like I said, this is very active research. And I'd just like to say on behalf of Canadian astronomy, thank you. My work today has used the Sloan Digital Sky Survey. It's used the Gemini telescopes, the International Gemini telescopes, one in Hawaii, one in Chile. Uh, I've showed you work on LRDs from the James Webb Space Telescope. Uh, the Canada, France, Hawaii telescope is featured in my work much in the past. The Hubble Space Telescope, of course, Canadian involvement in all of these, as well as the Square Kilometer Array Observatory of Radio Telescopes and the proposed CASTOR, Canadian-led ultraviolet imaging and spectroscopic telescope that we hope that our government will support and that you will support if you hear about it. And there's others as well. I don't have time to go through them all, but Canadian astronomy is active in producing cool science for me to share with you because of your support of Canadian astronomy. So thank you. And now I will take any questions.
Oh, thank you very much, Pat. This is a great talk. So much fun. And of course, I totally agree with you on the little red dots. There's so many wonderful things you talked about, including quasar properties, spinning, moving, and since it's October, gobbling up stars and gas and dust. Here's hoping that some of those mysteries prove solvable. Let's go ahead and check our questions over from YouTube. So just as a reminder, if you're on YouTube watching right now, put your questions in so that we can ask them to our speaker. Our first question is already here, so I'll go ahead and start with that. This is from Guy Yanez, who asks the question, quasars are expected to be be shifted due to their high temperature. Some are shifted because the light is falling into a black hole, but is it because they are far away and the universe is expanding?
I skipped over that. Let me go back. Uh, One of my figures might be helpful here. Yes. Um, so quasars in general are redshifted. So what we have along the top here is the wavelength scale in this antiquated unit called angstroms that astronomers use. Uh, in the rest frame of this quasar, so in the quasar itself, it's emitting from 1,000 to 6,500 angstroms. Uh, when we observe it, we see its light at 3,500 to 25,000 angstroms. So this light has been redshifted by about a factor of 3.5. And so, because the universe has expanded by a factor of 3.5 since this object emitted its light has gotten stretched by that factor of 3.5. And at the same time, when the quasar was emitting its light, it blue shifted some gas, and um, that absorption appears at a blue shift in the quasar frame. We see it redshifted because of the expansion of the universe. But to study quasars on the same basis, today and at this redshift of 2.5 and at redshift 7, we shift everything to the rest frame of the quasar and then study them. And so we take out the redshifting caused by the expansion of the universe and only worry about, whether the absorption is redshifted or blue shifted, so we can study it that way. So the blue shifting comes from acceleration um, from radiation by the quasar. The red shifting comes from the expansion of the universe. So I hope that helped clarify.
Well, I hope so too. It looks like we have a question from someone else. There is our next question. So hopefully, if there are more questions, they will come in as well.
Sure.
The next question is actually from Joshua Parsons, who asks, "Do we have an estimated distance epoch for the LRDs? What
Mm.
would their evolution look like? Would and then in parentheses, would they supernova or shed their outer layers, etc.?"
That's a good question. I'll mention this Redshift 7 LRD seems to be a sort of typical epoch. People have found things which look kind of like little red dots at low redshift, but most of them seem to be at high redshift. So we can think of the perhaps the first billion years of the universe um, was the era of little red dots, and then from maybe 1 to 3 billion years was the era of quasars, and after that, it's been the era of galaxies. That's very, very rough, but it is true that even though you can find some little red dots at lower redshift, and you can find some quasars relatively close to us today, they're very few and far between. Quasars were a lot more common 10 billion years ago, and little red dots were a lot more common 13 billion years ago. Whether what would happen when uh, how they get rid of this gas and dust, that's an open question. They wouldn't supernova, a black hole, a million solar mass black hole with all this gas around it, wouldn't supernova, but it is possible there could be some dramatic ejection. We see gas reaching 30% the speed of light and even a little faster in the X-rays. I imagine there will be people looking for events where we're seeing a little red dot shed its cocoon. So yeah, good questions. We haven't seen that yet, but I bet people are looking for it.
Fingers crossed.
Yep.
All right, so we have a few more questions rolling in. So next is from Omar Mikati, who asks, "What is the difference between LRD and other small red quasars?
Mhm.
Essentially, what makes it a dot?"
Well, the name Little Red Dot came just from that's just what they look like in these images from JWST. Um, what makes them different is a couple things. One is the fact that this reddening happens where it does, that it's reddening and absorption at a particular wavelength, and then some recovery of more blue light. The first, the image I showed you earlier of a reddened quasar, the light was just going all the way down. And that's easy to see that if you have dust around a quasar, dust affects shorter wavelengths more. And so you put some dust around a quasar and it's going to get fainter and fainter the shorter wavelength you go. But there's an effect here where this absorption is caused by very dense hydrogen gas, maybe not with a lot of dust. That was one of the early issues, is that the amount of dust that you need um, to redden these LRDs led to predictions of very high masses for the black holes, um, sorry, or the galaxies, or both. It was a bit of a problem, and now we think that it's some dust reddening, but it's also just a lot of absorption from gas. So I had to talk it through, but I can summarize by saying that in a reddened quasar, we think the reddening is coming from dust primarily. In a little red dot, we think this red dip here is caused by absorption from very dense gas in this cocoon of some sort around the black hole.
Awesome. And that is, it looks like we have time for maybe just one more question. So I'll go ahead and put this one in as well. We have user Asalamatov who asks, is the backside of the accretion disk, oh, I think this is a little typo. Maybe should the backside of the accretion disk be blue shifted since gas is falling to the black hole toward us and the front of the disk red shifted for the same reason?
Um, so there's lots of effects going on. Let's see if I can summarize them. You can see, um, so it is true that there will be a gravitational red shifting effect that the light, if we go back to our sodium lamps, if we just position them all through the accretion disk, the light emitted from close to the black hole will be red shifted due to gravity. And that's true on both sides of the accretion disk. It's really just a radius effect. Whatever your radius is close to the black hole, you get the same gravitational redshifting. The other effect that goes on is this spiraling, um, and you can sort of see it, although it's not quite clear, that the each of these um, you know, segments is the same area, but they get sort of concentrated here and spread out over here. And the spinning black hole sort of focuses light more. Focus isn't quite the right word, but it concentrates light. So one uh, part of the accretion disk, the approaching part of the accretion disk, looks brighter than the part that's going away. And that's not a blue shifting exactly. It's just well, I shouldn't say that. There's blue shifting because it's coming towards you, and red shifting on the other side because it's coming away from you. The blue shifted side will also look brighter than the red shifted side. That's really a special relativity effect. So there's all kinds of effects going on here that make it hard to calculate exactly. But gravitational redshifting, just a function of radius. Um, uh, Boosting just due to speed, and so blue shifting uh, from the part of the disk that's approaching us, and red shifting from the part that's going away. So I hope that covered most of your question there.
That's an excellent answer, and I know that I'm sure a lot of our folks will have questions that we aren't able to get to this evening. But it is about time to wrap up the question section. So I'm going to go ahead and thank our wonderful speaker once again. Thank you, Pat. It's a perfect spooky season talk that we've done here tonight, and I think we could stay here for quite a while talking about it, but we won't because we want to go check the Blue Jays score. So we'll go ahead and wrap up, and I'll go ahead and get the last transfer of the evening. So thank you very much to Dr. Patrick Hall for coming this evening and regaling us with quasars extraordinaire. Now we have one last transfer for tonight, and we're going to go ahead and send off the end of this show with a wrap up by the president of the RASC Toronto Centre, Scott Masterton, to finish off the evening. Over to you, Scott.
Well, thank you, Elena, and thank you for all our viewers that joined us tonight. My job now is to inform you about various events that will be of interest to you, uh, and also to let you know what we do tonight. Of course, tonight we had a speaker, and then in another couple of weeks we'll have a recreational astronomy night where our members come forward and explain various things that they've done, photographs, investigations, and so forth. And before each event, speaker night, RAN meeting, the Carswell Observatory will be available for people joining us in person, and you'll need to contact Elena to get more information. The Carr Astronomical Observatory in Collingwood, our observatory property, is available to our members, and it's available year-round. We've managed to arrange to have the road plowed year-round and cleared. But of course, you'll have to make an appointment and make bookings at the web site indicated. And in order to go there, you have to be a member. So we would invite you to go to the national office website and obtain a membership there. Of course, once you've done that, you can be a volunteer, and you can assist us in various endeavors that we take on. Contact the volunteer coordinator. The events that are upcoming, because there were Messier Marathon weekends were clouded out, we are mounting a star party at the CAO the weekend of October 24th to 26th at the Carr Astronomical Observatory, members only. It's a closed event, no fee is charged. Book your space. The Millennium Star Party, October 24th or 5th, is available in Pickering. We would invite you to bring your own telescope, where you can get assistance in setting it up. The fee is free, and that will be October 24th or 25th, depending on the weather. The DDO has Sunday stargazing on October 26th. You can safely view the stars, our star, the sun, at the Dunlop Observatory, and registration is required. Details are at rasto.ca. Recreational Astronomy Night, November 5th. That will occur Wednesday, November 5th at the university, and it's an in-person and online. Everyone is welcome, no fee, and no registration required. Location, of course, York University. And our next speakers night, November 19th, we will have Professor Charles Edward Bourquet, a York University professor. And his title is Structure, Composition, and Internal Dynamics of Rocky Planets. The fee is free, and it begins at 7:30. Registration not required. Get the details at rascto.ca. And have a good night. Thank you for joining us.